This is OPTI 380A, final project, Interferometric Optical Test Bench. I'm Sedona Skyzeller.
I'm Ethan Luker.
I'm Jack McNeilis.
I'm Brandon Leonardo.
I am John Kellerman.
I'm Sofia Centeno. Our TA is Abar Liaf, and our faculty companion is Dr. Jose Sassian.
Interferometry is essential in physical optics because interference fringes let us measure optical surfaces and wavefronts precisely. For our final project, we aligned a Zygo Verifire Fizeau interferometer to test flat and curved optics, including a plano-convex lens. Our motivation was to connect interference and coherence to optical metrology used in commercial optical testing and research by studying measurement accuracy, alignment sensitivity, and repeatability.
Light exhibits wave-like behavior as it moves through space, which means it has a phase and amplitude. When two waves of light are in the same spot, they add together and can interfere with each other, producing bright or dark spots if in phase or out of phase. If a single light source is used, these phase differences can be caused by differences in distance traveled by different rays of light. These path length differences can be caused from things like the non-constant thickness of a soap bubble, the roughness of a surface, or the focusing power of a lens. We can exploit this to make extremely precise measurements of optics using a process known as interferometry.
All measurements were taken using a Zygo Verifire interferometer with a 632.8 nanometer helium neon laser. Depending on the surface measured, either a reference flat or a transmission sphere was used to create a corresponding reference wavefront. We took measurements of the three different surfaces, a flat surface, concave mirror, and a plano-convex lens. From left to right, the setup included the interferometer, the test surface mounted on a translation stage, and a flat mirror at the end of the optical bench. This layout made it easy to control the position of the test surface while keeping the reference wavefront stable. Interference fringes were recorded with the Zygo camera, and surface values like RMS and PV error were taken using the interferometer software.
Using the Zygo interferometer at 632.8 nanometers. This system was aligned by inserting the transmission sphere into the interferometer and adjusting its alignment knobs until the interference pattern was centered and measured in alignment mode. Final alignment was achieved in view mode by adjusting the optic mount until clean, stable fringes were observed. For measurements, and a translation stage with a digital micrometer was used to locate cat's eye and confocal positions. Interference data, including RMS and peak to valley, were recorded using the Zygo analysis software.
This is the results and data analysis section. When measuring the flat surface, we found a low RMS error values indicating stable alignment, while the PV error showed some measurable surface deviations. We also measured a concave mirror and found its average radius of curvature to be negative 204 millimeters with a relatively low variation. Next, we measured the focal length of a plano-convex lens using the coordinating method, finding an average focal length of 83.41 millimeters. Standard deviation was 0.553 millimeters, with the uncertainty mainly being from identifying collimation point. Finally, we measured the reduced thickness of the plano-convex lens using the interferometer and the average radius of curvature using the spherometer, yielding an index fraction of about 1.53, consistent with MBK7 glass.
We met our objectives by learning to align the Zygo interferometer, measure flat and curved surfaces, and apply Newton's and Cornu's methods. Results were consistent. Limitations included sensitive alignment, subjective collimation, and reliance on approximations. Improvements could involve finer mounts, automated alignment, and cross-checking with other methods. Future extensions include testing aspherical or multi-element optics, varying wavelengths to study chromatic effects, and automating data collection. All group members contributed through planning, alignment, data collection, and analysis to ensure strong understanding of theoretical and experimental methods.